So my name is Bruno da Silva Lopes, and today I'll talk about a recent work we published this year titled Hot QCD at Finite Isospin Density, Confronting Effective Models with Recent Lattice Data. So I'll follow this outline, and this work was done in collaboration with Professor Ricardo Farias, uh, Aritra Bandyopadhyay, Diana Duarte, and Sidney Avancini. So the object of study here is quantum chromodynamics. It's the theory of the strong interactions between quarks and gluons. And the study of QCD is interesting because it brings many implications in many physical systems, such as the quark-gluon plasma, heavy ion collisions, or compact objects. So to talk a bit about QCD, we can study the QCD phase diagram. Here we have the temperature in the vertical axis, the baryon density in the horizontal axis, and the third axis with the difference in the number of neutrons and protons. So at low energies, such as low temperature and low baryon density, QCD presents a property called confinement. So the quarks are confined inside the hadrons. But at high energies, we know they formed the so-called plasma of quarks and gluons. So for low baryon density, this transition is well known due to lattice QCD results. We have a crossover between those two phases. But for high baryon density, we cannot study QCD on the lattice. So we have to make predictions with effective models. And of course, here, the main object of study, we can have systems in which the number of neutrons and protons is not the same. So we work on finite isospin density. Okay, so we cannot study lattice QCD at finite baryon density because the fermion determinant becomes imaginary. And when we try to perform Monte Carlo simulations, there is no positive weight in the path integral. So we need to find other ways to solve QCD in this regime. And finite isospin density, why is it relevant? So an isospin asymmetry can be present when there's an excess of neutrons over protons or vice versa. And the isospin density is defined in equation 3 in terms of the quark densities. And this can be relevant in physical systems such as neutron stars, obviously, and heavy ion collisions. And the most important thing here for us is there is no fermion sign problem when working at a finite isospin chemical potential. So we have lattice QCD results to use as a benchmark for comparing the predictions of our effective models. So, as we said, there has been recent lattice QCD results on this subject. The authors also predict a new class of compact stars called pion stars. So this is an ongoing subject. We also thank Brunt and Andrade for the help with the lattice data used in this work. And okay, so we want to work here in the Nabula-Jonalesini model of three flavors. Equation 4 is the Lagrangian density of the model. We have here psi is the quark spinor. M is a diagonal matrix of the quark masses, and defining the chemical potential matrix, we can evaluate the partition function. and those chemical potential of the individual quarks, they can be expressed in terms of the baryon chemical potential mu b and the isospin chemical potential mu I. In this work, we'll limit ourselves to 0 mu b and finite mu I, and also 0 strangeness chemical potential. So in the mean field approximation, defining the sigma condensates and the pion condensate delta, we can obtain the thermodynamic potential. And so the important part here, can also define the effective quark masses generated by the chiral symmetry breaking. So the integral of the first three terms in equation 9 is divergent. So we need to apply a regularization scheme. And in this work, we compare the results of two regularization schemes: the traditional regularization scheme, TRS, which consists in integrating up to lambda, the first three integrals, and the medium separation scheme, which I'll explain a bit more here. We can work with these terms, and the MSS, it's a way to disentangle the finite medium dependencies from the vacuum divergent contributions. So if you see here in these terms, we have the effective quark masses. And when we work on the MSS scheme, the only integrals on the thermodynamic potential will depend only in the value of the mass in the vacuum. So we're not cutting in lambda the finite medium dependencies. So to find the physical solutions of the condensates, we solve the gap equations, minimizing the thermodynamic potential. And the thermodynamic quantities are defined as the pressure is minus the thermodynamic potential. The isospin density is the derivative with respect to mu I. We also define the energy density and the interaction measure or trace anomaly, I. So to obtain numerical results, we need to use a parameterization. In this work, we use set 1 for the zero temperature case and set 2 for the finite temperature case. And here we fit the values of the pion decay constant,
2 minutes.
the masses of the pion, the decay and eta mesons, and the mass of the light quarks. So the first result in zero temperature, we compare the chiral and pion condensates as functions of the isospin chemical potential. Here we can see the onset for pion condensation is when mu I is equal to m pi. And at this chemical potential, the chiral condensate starts to decrease and the pion condensate is formed. Also for higher values of mu I, the MSS and TRS schemes begin to show a bigger difference. Here we see the normalized pressure as a function of mu I. I'll focus here on the NF equal to +1 or three flavor results. So for this picture, the MSS result seems closer to the lattice QCD results. Also for the isospin density as a function of mu I, still at zero temperature, we have at low mu I, the MSS, the green dots, seems a better fit, but at higher values of mu I, the blue dashed curve seems a better fit for the lattice points. Here we show the energy density scaled by the Stefan Boltzmann value. And here we can see the Stefan Boltzmann limit in this picture here can only be expected to be achieved when using the MSS formalism. Here you also see the interaction measure at t equals 0. Again, the MSS results in a bit closer to the lattice, but a very small difference. Now, at finite temperature, you can see here the condensates against temperature for mu I equals to 206 MeV. So the condensates melt with temperature, and biocondensates is a second order phase transition, and chirocondensate seems a crossover type of transition. Again, the normalized pressure for mu I against mu I for two values of the temperature. The TRS here seems to be a little better fit for low temperature, while the MSS seems a slightly better fit for high temperature. The same will occur here when comparing the isospin density. And for the interaction measure or trace anomaly, we can see all the results are within the band for low temperature. And for high temperature, the SU3 results are slightly off, but the MSS results get closer to the lattice for high mu I. So this is the phase diagram for chirosymmetry breaking or restoration and pion condensation. The TRS results are closer to the lattice, but the critical point, the pseudo triple point, seems to be in slightly better agreement with MSS. So for perspectives of this work, we'll try to implement it considering the Polyakov loop extended NGL model. And we want to build an equation of state considering an isospin asymmetry. We thank Andrade and Brandt for discussions and for providing the latest data sets. And also thank the CNPq, FAPERGS, and CAPES for the support. And thank you for your attention.